opportunity to talk about this work. I will start with some background underpinning this contribution. So I will talk about traditional finance theories, their assumptions, the contributions of the behavior finance scholars, in particular in respect to the non-Bayesian mode of information processing by investors, and how important are the investors' expectations in actually shaping asset prices. I base my talk on a paper where we introduce a model borrowed from the theory of open quantum systems. Can be considered as contribution to econophysics from the side of quantum probability, quantum physical models, to incorporate the more deep, so to say, uncertainty that can be captured by, that can be potentially captured by quantum models. We also presume that asset prices can interact more intensively than understood by classical statistical correlation, and use the notion of entanglement to capture this phenomenon. This is a theoretical model. There is no endeavor to, in any instance, replace a classical traditional approach to asset pricing. It is just a contribution which could be potentially applied by practitioners to incorporate agents' expectations into asset prices. Before I start, I would like to present some general background to the field. This is not, of course, the whole list of contributions where here we can try to make a bridge between classical econophysics and quantum finance, quantum econophysics, where we have such a pioneering contributions by Prof. Haven, Prof. Baku, who published a book actually on quantum finance, and also has many contributions on modeling interest rates and solving quantum framework. So we have also a list of other contributions where those two papers by Asana and his colleagues are actually using this dynamical model for this quantum master equation. It's in its very simplified form to dynamically capture agents' belief evolution in various contexts. One of the contributions is in a prisoner's dilemma game. So they try to capture this non-Bayesian processing of information over time via this model. So the field is emerging. Of course, there is a need of additional empirical evidence, which is, of course, the main challenge, but the field is growing. So let me start briefly by outlining, so to say, the assumptions. Of course, everyone knows it, so it's more of just a short, so to say, background, short context, why we think that this model can be, have potentially some future. Traditional finance models are built, of course, upon three main blocks. This is the model portfolio theory by Markowitz, upon which we have the capital asset pricing model that gives us the expected returns that rational investors should have from holding assets, from adding an asset to a market portfolio. There are different extensions, of course, such as Fama-French three-factor model and other various related factor models. The main assumption behind the Markowitz model portfolio theory is that each investor is able to access the probability distribution of the assets returns, and so all the investors have homogeneous expectation in terms of variance and expected return and they can make a full, so to say, subjective updating of information, which follows the rules of classical probability theory. So this is a very important assumption. And we have two moments which the investor is interested in, is the expected return and the standard deviation. And if we add this asset to a portfolio of assets, we deal with beta, which is measuring the systemic risk of this additional assets. So this is, so to say, I think the core theory that we use in all the models where we discount the future cash flows, future dividends. We use CAPM in order to obtain the expected return on an asset that we hold together with a well-diversified portfolio. And this is only one factor which is important in order to, so to say, be able to assess the expected return on an asset, which is the beta. This is a measure of how much systemic risk the asset adds to the well-diversified portfolio, the market portfolio. So this was just a short review. Of course, the explanatory power of CAPM was not that great, so there were many modifications, mainly in the area of adding additional factors, such as a small company risk premium, book to market, and various other advances, where behavior finance scholars started to place increasing emphasis on what agents think should be the fair return, what agents think should be the price of the asset, which they showed could deviate from the fundamental value. Also, we bring in efficient market hypothesis that works together with CAPM. So I can mention two models that were aiming to address this issue of agents' expectations and irrationalities. This is the so-called behavior CAPM by Sheffrin and Statman, and very recently an excellent contribution by Mokhar, who also found out some additional behavior factors that could, so to say, explain actual returns. These models were basically trying to overcome the challenges posed by non-homogeneous expectations and the exhibition of various biases. So the main question that the behavior finance school were asking, and this was increasingly appearing in the literature, the question was concerned with risk. So is risk exogenous by its nature? Is it just the variance? So it is externally given, and we are not anyhow participating in creation. Should we just worry about variance, or only worry about downside risk, downside volatility? So those were all the questions that emerged, and the important thing was that agents can be uncertain about future states of the world. They cannot always base their future expectations on historical information, and I would say that the recent periods are characterized by much more increased uncertainty, which we faced after the financial crisis. So the main assumption also that we try to incorporate in the model is that the prices are a result of expectation of agents, not always the fundamental values of the assets. And in some instances, the expectation of agents can bring these prices to fundamental values. This is what actually efficient market hypothesis says, that the irrational investors are trading, but their actions are canceling out each other, and so to say, we still get an equilibrium price. But in other periods, we can witness a so-called common bias effect, where many investors are basically reacting in the same direction in terms of their information processing and overtrading and so on. So here I just present a short, not a short, a graph from Robert Shiller's Irrational Exuberance, where he collected actual share price of the Standard & Poor's 500 index over a long period of time and compared it to, so to say, what should be the fundamental value of assets if, for instance, the investor discount the future dividends or the future earnings of the assets that compose this index. We can first of all witness that the actual price is characterized by much more increasing volatility, so there are much more spikes and downfalls which are not explained by the anticipated earnings and dividends, but secondly that in many periods, in fact, the assets are overpriced by agents, which is a bit difficult to explain by the earnings and dividends that the agents anticipate. Okay, let me move to the actual model now, which I will not go into much detail, but just explain what is the, so to say, assumption. So it is a usage of quantum framework. The asset prices are modeled in a Fock space, so each asset has its own state space, which we can start by an infinite dimensional space, but of course based on historical observation to start with the range of prices that have been observed for each particular asset. The state space can be fixed empirically. So if we would like to talk about, for instance, so this is a toy, of course, example. We have some asset A1 and A2, and obviously each of them can have various price configurations. And in this state space, we can, for instance, represent for two assets that the agent's expectation about the assets' prices would be a superposition, a state vector characterized by all the particular combination of possible outcomes, which C are the complex amplitudes, and those are the basis vectors associated with each price configuration, with each eigenvalue that the asset price can take. So this is, so to say, the basic. What is the, so to say, difference of this model to a classical probabilistic model is that we depict a so-called more deep uncertainty, quantum uncertainty. So we have a state of superposition where the outcomes, so to say, can coexist in the agent's mind, and no concrete probabilistic distribution can be assigned at the moment of time. So I think mentioned some of those aspects here. So we can adjust the state space when we can model, for instance, of course it becomes, the complexity increases, but we can have accommodate n financial assets where the eigenvalues can be in the form of some natural numbers. So we can have, for instance, monetary units associated with the asset prices. This is, of course, a simplification, so we have to round up the asset prices to some concrete, so it's the discrete price states. So for a single asset, we have a Hilbert space which accommodates all the price states of this asset. And for the moment of time, the asset is in a superposition of all those different prices. So we have also an indeterminacy about future prices, which is actually even more deep than the classical one, because all the future, so to say, price configuration coexist in this space.
But coefficients are time dependent. These C coefficients are time dependent.
In the model, there will be time dependent when we add the dynamics. Yes, now I just talk about geometric properties of, so to say, of the space of single assets. So this is the space of single asset, and then of course, if one wants to, so to say, enhance the model, to complicate it, the asset can be combined through a tensor product. This asset state spaces for single asset can be combined via a tensor product, where we get, so to say, this composite stat space, which is the Fock space of all the assets. Okay, this is, of course, this assumption needs to be validated, but it has been already, so to say, widely explored in decision-making context, that states of assets can be statistically more strongly correlated than the classical correlation understood in classical finance, where we can have a so-called entanglement. Entanglement is a quantum notion, which means that states of two, if we take two electrons and so on, so if we observe one of them in one state, then the other one will be automatically observed in the other state, which means that they have a very strong, so to say, very strong correlation, that the one is automatically, so to say, bringing the other outcome. This is a quite complex notion, and I'm not a physicist, so here I'm using a more of operational framework to see that possibly the asset prices could be correlated in quantum physical way rather than in the classical statistical way. All right, so what is then the idea, so to say, of this model? The idea is that we would like to observe some, in the long term, some equilibrium state, which can be generated by the approximation of the quantum master equation, Khrennikova-Sudarshan-Lindblad equation. This model has been used for decision making of agents quite substantially, so we decided to adapt it also for using it for modeling the dynamics of, so to say, asset price states. If we would just use Schrödinger equation, then we would not have any stationary solution. We would not have any stabilization of the quantum state to a classical state in terms of a matrix with classical probabilities. And in this more extended model, we are able to capture, so to say, this interaction with the path of investor expectation is, of course, captured in some numerical value now. Is a bit abstract, where the main advantage is that we can, so to say, obtain some limiting distribution of the probabilities associated with each price state, and this would be the long-term prediction. So the output of the model would be in terms of the time, so we can add a real time scale of the asset price stabilization and of the probabilistic distribution associated with each price state. I don't know if I have time to. So the form of this model is if we just remove the Lindblad term, we will deal with the classical Schrödinger equation. This is just those additional linear operators are added in order to actually capture the interaction with agents' expectations. So the asset prices are interacting with agents' expectations. The reduced Planck constant is replaced by just a scaling parameter I, because we don't know, really we are not able to measure the notion of financial energy, so it's a bit difficult topic to measure, so we just use it as a time dimension, just as a scaling constant. All right, there was also a simulation in Mathematica to show that, so we can get a classical probability distribution finally to observe the price in a particular state. Okay, let me jump. I know I'm a bit fast now, so let me just finish now with what are, so to say, the main assumptions or the main proposal of this model. So we assume that agents can be irrational and not process information homogeneously. They can be uncertain about the future price states, and their beliefs and expectation can interact on an informational level with the asset price states. So this can be potentially modeled in a quantum framework, this so to say non-classical uncertainty, where one could, by of course collecting some empirical data, here we just use some parameters just to show these dynamics, get this, arrive at this prognosis of some asset price. So this will be a classical probabilistic distribution of asset price configuration, which could aid, I don't know, experts or practitioners. There is, of course, work to be done. So, okay, I think I have now to finish because you showed me the time several times. And thank you so much for your attention. Right, I'm done.
Thank you very much, Polina. So now it's time for the room to ask questions or to suggest some comments. So, yes, Peter?
Yes. In physics, quantum mechanics has this constant h bar, and it is a constant.
Yeah.
Well, I think, unless one gets into general relativity and all of that, I'm not sure. But by and large, it's a real constant. It can be measured to hundreds of decimal places and that kind of thing. And one knows what it is, roughly, you know? Relates to uncertainty and position and momentum, that kind of thing. What does your equivalent of h bar relate to? And is it a constant over time, for example?
This is a good question, because obviously we cannot use we could not quantify any financial energy. I don't know how to, so to say, to use this time energy dimension. So in additional in another contribution, we just use it equals to 1. Why? Just
so you assume it's constant?
We assume it's constant. Yeah, it is, I think, still work to be done to derive it an analog, because we just...
Something has been written on using h, so the equivalent as a scaling parameter.
Yeah, you just scale it.
I'm trying to remember which paper. It was a paper by...
Yeah, Michel?
I have a question. You mentioned that you favor situation or concept when system equilibrate.
Yeah.
Then you decided for this.
Yeah.
But I think that also you could consider, my feeling, situation or concept where no stationary state is present. So both, as I correctly understand, you do not exclude any of these here, because, okay, sometimes situations that you reach equilibrium, definitely stationary states should exist, but right now,
this is true.
Perhaps.
So, yeah, the parameters were chosen that the system is approaching a stationary state. But if you use other parameters, actually, it is there in the picture. The state cannot be reached. So this is the stabilization to classical state.
So the main logic of application of quantum is that it's tree-value logic, interference logic. Mm-hmm. Between object there is interference, and that you must introduce analog of wave function, psi function or something. So tree-value logic. Because of, so the probability. Now you different way to calculate probability. Not classical, but you need this interference way to calculate probability. So that's a lot of consequences, very deep consequences.
Yeah, of course, I think it's well known in the literature that even via double-slit experiment you can show that, of course, there is.
So thank you for this inspiring talk.
Okay, thank you. Yeah, but you're completely right about the non-stationary can also exist.
Other questions, comments on the paper presentation? Yeah, Emmanuel?
Compared to the paper in political science, does it give you more insights if you apply this within this financial context?
I think I see here a problem. Of course, I would not start with criticizing it, but I see here a problem, of course, that in political science, the model is modeling the beliefs of the voters, so it's a bit more easy. Here is a very operational, so the state of an asset is a purely operational concept where you can, of course, not assume that the asset can anyhow by itself be in different price configuration. So this, I think, should be just used operationally at this stage to maybe feed the data and so on.
Yeah, another question? Yeah, we're done.
Maybe a little bit related to what Peter said. So in true quantum mechanics, you have, of course, this Planck constant, which, how to say, divide your word for classical quantum. It's a resolution. But the question is it possible, because it should suggest something, some constants which should distinguish between classical probability approach from this interference, so to say, interference probability approach. So it should exist some kind of threshold or some kind of between these two logic, because classical logic is very special case, of course, but nevertheless, it's perhaps. Do you think? Have you some intuition, or it's such constant, such universal, or does not exist?
I'm not sure if it can be derived empirically from psychological data. Is not easy to match it like apple to apple. So the problem is, of course, that it's very difficult to derive it, because we all the time have to use different Hamiltonians for different models.
You suggested something, because that risk and price, so or return, risk and return. So return increase and risk increase. So I see an opposite direction. So there is some. So we should look for some coupled dynamic quantities, and then look. So make table of this thing, and then look whether exists such coupling between these dynamic quantities.
Yes, I think there is, of course, work to be done to scale it to this phenomena. We borrowed it, so I borrowed in this setting from a paper on politics, on voters' behavior, where we use a scaling one, and it gave good results. But context is completely different, of course. So as you say here, we have more data, actually, when we can use price configuration and risk also. But thank you so much for your suggestion.
Yeah, another question?
Okay, when we use differential equations to predict future, we always know that's a difficult job. Are you aware of any back data testing type of work carried out for using quantum mechanics models?
In this particular paper, not, but there are contributions, yes, that did for decision-making problems. So they measured the final probabilities distribution of decision makers in different contexts, and then they tried.
Is it long-time, medium-term, or short-term predictions?
I think please. People from quantum community correct me if I'm wrong. I think in Photos and Bussemer papers they use Schrödinger equation, though, so they were interrupting the dynamics by, so to say, setting a threshold in time. They, I think, were assuming that there is a particular time that a decision maker needs to take the decision. So after this threshold, they were just interrupting the dynamics and looking at the probability distribution. But here, of course, the scale is much bigger. So it is a bit difficult to fit the real scale. But it can be tuned, of course, with parameters if you play more with the parameters.
All right. Maybe the last question? We still have time for one question? Or is it okay? Well, if you are okay, then thank you again, Polina.